Part 14. Field Configuration Rules, from local ripples to global fields. Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are nearing the summit of Book 9.3 in Episode 9, The Generative Grammar. Our journey through wave and field generation has been a profound ascent. We began by learning the alphabet, the dispersion relation that defines allowed wave tones. We then formed words, localized wave packets that travel and evolve. We discovered grammar, the interference rules that create beautiful, stable patterns when waves overlap. But so far, we have been describing temporary meetings, passing conversations between waves. Today, in Part 14, Field Configuration Rules, from local ripples to global fields, we witness something transcendent, the emergence of permanent dialogue. We discover how waves can stop merely passing through each other and instead lock together, creating sustained, coherent fields that span vast regions of space and time. This is how the universe writes paragraphs, chapters, entire narratives, not just isolated sentences. Our anchor image is a vast stadium at night, filled with tens of thousands of people holding smartphones. Initially, the lights are on randomly, a twinkling, chaotic sea of individual points. Then, a signal is given. One by one, sections begin to coordinate. Not all at once, but through local communication, person to person, row to row. Slowly, miraculously, the entire stadium becomes synchronized. The random twinkling transforms into a single, massive, sweeping wave of light. A coherent pattern emerges from this order. The individual lights haven't vanished, they still exist, but they are now acting as one giant, coordinated field. This is the leap from local ripples to global fields. Today, we learn the grammatical rules that allow phi to perform this same miracle, creating lasers, superfluids, ferromagnets, and the very ground state of ordered reality. Here is the profound puzzle of this part. We understand how individual waves behave and how they temporarily interfere. But what are the rules that allow wave-like patterns in phi to become locked together over extended regions? How does local coordination propagate to create global order? And what determines when such coherent field configurations are stable and allowed by the grammar versus when they fall apart into chaos? The answer lies in the concepts of correlation, coherence length, and spontaneous symmetry breaking. These are not new substances, but deeper grammatical rules about relationships within the phi field. First, correlation. This measures how much the value of phi at one point knows about, or is related to, the value of phi at another point, even far away. In a completely random, uncorrelated field, like the initial random twinkling of phone lights, knowing phi here tells you nothing about phi there. The correlation is zero. In a perfectly coherent field, like the synchronized stadium wave, knowing phi here tells you exactly what phi is there. The correlation is perfect and extends across the entire stadium. The field configuration rules specify how correlations are generated and propagated through the dynamics of phi and its interactions. Second, coherence length. This is the physical distance over which phi remains correlated. It is the size of the patches within which the field is singing the same tune. In the random light scenario, the coherence length is essentially zero. Each light is independent. In the synchronized wave, the coherence length is the size of the stadium. It's global. The coherence length is not static. It can grow or shrink depending on conditions. The field configuration rules predict how the coherence length depends on the parameters of the system, like temperature, density, or driving strength. Third, spontaneous symmetry breaking. This is the elegant mechanism by which a globally coherent field chooses a specific theme or phase. Imagine the stadium could create a wave moving clockwise or counterclockwise. Both are equally valid solutions to the rules of coordination. Initially, the system is symmetric between these possibilities, but as coordination begins, local random fluctuations get amplified. One small group starts a clockwise wave. This choice, once made, biases its neighbors. The coordination propagates, and soon the entire stadium has, spontaneously, chosen the clockwise pattern. The symmetry between clockwise and counterclockwise is broken. The field has settled into one specific, coherent configuration, even though the grammar itself didn't prescribe which one. This is how a laser chooses a specific phase, how a magnet chooses a North Pole direction, how the Higgs field chooses a value throughout the universe. Let's explore the triunity of field configuration. The time echo of field configuration, persistence and memory. A coherent field configuration exhibits long-term temporal stability. It's not a fleeting interference pattern, it's a persistent state. A laser beam doesn't flicker randomly. It maintains a stable phase for remarkably long times, its coherence time. A superfluid flows without friction forever in a closed loop. The time echo is this enduring rhythm, a locked-in vibration that resists decay. This temporal coherence allows for precise frequency standards, atomic clocks, and the stable operation of quantum computers. It is time itself becoming regular and predictable over extended durations. The space echo of field configuration, extended order and structure. A coherent field imposes spatial order. In a ferromagnet, the magnetic orientation, a derivative of phi, aligns over macroscopic distances, creating a uniform magnetic field. In a Bose-Einstein condensate, millions of atoms occupy the same quantum wave function, meaning their collective phi field is described by a single, smooth phase pattern that can be centimeters wide, huge on the atomic scale. The space echo is this global architecture, a single pattern spanning vast distances, making the system behave as one giant quantum object rather than a collection of parts. The motion echo of field configuration, collective dynamics. When a field is coherent, its motion becomes collective and often frictionless. In a superfluid, the entire fluid can flow around obstacles without viscosity. The motion is orchestrated by the gradient of the single coherent phase. In a laser, photons are emitted in lockstep, creating a beam that diverges very little and can be focused to a tiny spot. The motion echo is this unified, efficient flow. Energy and information propagate with minimal loss and distortion because every part of the field is moving in concert, not fighting against itself. Now, let's locate this culminating node on the master tree. We are at the coherent field formation branch, the highest limb of Book 9.3, Waves and Fields. This branch depends utterly on all the previous wave concepts: dispersion, to have well-defined waves; packet generation, to understand localization; and interference, to understand how waves combine. It enables the transition into Book 9.4, Dynamical Grammar, where we will ask why the universe prefers some field configurations, like coherent ones, over others, introducing the concept of action and cost. It also directly bridges the wave and particle pictures. A coherent field of phi, like a Bose-Einstein condensate, can exhibit collective behavior that looks like a single giant particle. To illuminate this abstract synthesis, let's place our lanterns across reality. A near lantern, from social dynamics, the synchronization of applause. At the end of a powerful performance, applause begins as a chaotic roar, uncorrelated clapping. Then, something shifts. You hear it. The claps start to synchronize. Local interactions, hearing your neighbors, create correlations. A rhythm emerges and spreads. The coherence length grows from a few people to the entire auditorium. The audience has spontaneously broken the symmetry of random noise and chosen a specific shared tempo. This is a classical, emergent coherent field in the social phi of rhythmic applause. The rules are the social coupling and the desire for cohesion. A middle lantern, from engineering and nature. The laser. A laser cavity contains a gain medium, like a crystal or gas. Initially, atoms emit light randomly, incoherent flashes. But the cavity mirrors reflect light back and forth. This reflected light stimulates other atoms to emit light with the same phase and direction. This stimulated emission is a powerful amplification of correlation. Once a slight coherence appears, it is explosively amplified. Very quickly, the system undergoes a phase transition. It switches from incoherent emission to a coherent giant wave, the laser beam, with a single phase and wavelength spanning the entire cavity. The coherence length becomes the distance the beam can travel without losing its phase relationship, which can be thousands of kilometers for precision lasers. The laser is a perfect technological example of field configuration rules in action. Local rules, stimulated emission, lead to global coherence. A far lantern from cosmology. The cosmic microwave background, CMB. This is the oldest light in the universe, a snapshot of the plasma field when atoms first formed. This light is incredibly coherent on a scale that defies classical explanation. Tiny, random quantum fluctuations in the primordial phi field, in this context the inflaton field, were stretched to astronomical sizes during cosmic inflation. These stretched fluctuations became the seeds of correlation. They determined where matter would later clump into galaxies. The pattern of hot and cold spots in the CMB is a direct image of these primordial correlations, the coherent structure of the early universe's field. The field configuration rules of inflationary cosmology precisely predict the statistical properties of this pattern, and stunningly, the measurements from satellites like Planck match these predictions exquisitely. Here, field coherence rules, written in the first moments, shape the entire large-scale structure of the cosmos. From synchronized clapping to the laser spew light to the blueprint of the cosmos, a unifying theme. Local interaction rules, when conditions are right, can cause correlations to propagate and amplify, leading to a phase transition into a globally ordered state. The system spontaneously selects a coherent configuration, and this configuration then dictates its large-scale properties and dynamics. What then is the specific language role of field configuration rules? They are the grammatical rules for paragraph and chapter formation. They govern how simple wave sentences, subject, verb, object, can link together through consistent themes, correlations, to form extended, meaningful narratives, coherent fields. They answer, under what conditions do many wave sentences combine to tell a single unified story? And what are the properties of that larger story? The core question this part asks about phi is, what are the conditions and mechanisms that allow a configuration of the phi field to maintain strong correlations, coherence, over large spatial and temporal scales? And how do these coherent configurations behave as unified entities? We are moving from the grammar of sentences to the grammar of narratives. What do these field configuration rules do in the generative process? They define the possible phases of matter, solid, liquid, gas, superfluid, ferromagnet, laser, as different classes of coherent phi field configurations. They predict phase transitions, the precise points, temperatures, densities, where coherence emerges or vanishes. They explain emergent phenomena like frictionless flow, perfect diamagnetism, Meissner effect, and long-range order. They provide the framework for understanding collective excitations like phonons in solids or plasmons in metals, as disturbances on top of a coherent background field. Now, stability and breakdown. Coherent field configurations are metastable or ground states of the phi dynamics. They are stable within a range of parameters. They break down at phase boundaries when temperature, pressure, or other control parameters cross a critical threshold. At this critical point, correlations become infinite ranged in theory, the coherence length diverges, and the system is maximally sensitive. Past this point, the coherent order is destroyed and the field becomes disordered. Correlations are short-ranged. Coherence can also be destroyed by decoherence, the loss of phase correlation due to interaction with a random environment. Within its domain of stability, a coherent field configuration is a robust, dominant feature of the system's grammar. This brings us to the rigorous heart of our discipline, falsifiability. The claim that coherent fields arise from specific correlation-generating rules in the phi grammar is a detailed predictive framework. The central claim: for any system described by a holophase field phi, the emergence of long-range order, coherence, will occur at critical values of control parameters, temperature, interaction strength, etc., predicted by the model. Furthermore, near this critical point, measurable quantities like the coherence length, the correlation function, and the susceptibility will follow precise scaling laws with predicted critical exponents. These exponents are universal. They should be the same for vastly different physical systems, like a fluid and a magnet, if they belong to the same universality class in the phi grammar. A concrete measurement scene, the superfluid transition in liquid helium-4. Helium-4 becomes a superfluid below a critical temperature of about 2.17 Kelvin. In the superfluid state, it exhibits frictionless flow and quantized vortices, which we've studied as topological defects. The order parameter for this transition is essentially the coherent phase of the macroscopic wave function, our phi field. Experimenters can measure the coherence length and correlation function as the temperature is warmed toward the critical point from below. This is done using techniques like neutron scattering or light scattering, which probe density fluctuations and phase correlations. They can also measure the superfluid density, the fraction of the fluid that flows without friction, as it goes to zero at the critical temperature. The pass condition, validation. As the temperature approaches the critical temperature from below, the measured coherence length diverges, grows toward infinity, according to a precise power law. Coherence length is proportional to 1 over critical temperature minus T raised to the exponent nu. The exponent nu predicted by the phi-based model for this universality class, the XY model, is approximately 0.67. The measured data fits this power law with the predicted exponent. Similarly, the superfluid density vanishes with a different predicted exponent. The critical behavior matches the theoretical prediction across multiple independent measurement techniques. This confirms that the field configuration rules correctly capture the physics of the phase transition into a coherent state. The fail condition, falsification. The coherence length does not diverge as predicted, but instead plateaus or follows a different functional form. The measured critical exponents consistently disagree with the phi model predictions across multiple experiments. Even more damning, if long-range order, for example frictionless flow, were observed above the predicted critical temperature in a clean bulk sample, it would falsify the current field configuration rules for that system. It would imply a different mechanism for coherence is at play, one not captured by the standard phi grammar of spontaneous symmetry breaking and correlation growth. Such a discovery would be Nobel Prize-worthy and would force a major expansion of the theory. This falsifiability ensures that our awe for coherent states, lasers, superconductors, superfluids, remains grounded in hard, quantitative, empirical validation. Let's cultivate a practical recognition skill. You can train your intuition to see field configuration logic in any system where local interactions lead to a sudden, large-scale change in organization and behavior, creating a new, unified phase with distinct properties. Observe traffic flow transitioning from free flow to synchronized traffic. At a certain density, cars are no longer independent. Through local following rules, they become correlated over long stretches of highway, moving in coordinated platoons or waves. The coherent field of synchronized traffic has different properties, higher throughput, stable speed, than the incoherent phases of free flow or jammed traffic. The transition is sharp and can be predicted from car density and interaction rules. Watch the formation of a crystal from a cooling liquid. As temperature drops, atoms lose independent motion. Local attractions cause them to align into a periodic structure. This alignment propagates. Suddenly, the entire sample freezes into a crystal, a coherent configuration with long-range positional order. The system has spontaneously chosen one specific crystal orientation among many possibilities. Consider the spread of a linguistic convention or a technological standard. Initially, many options exist: Betamax versus VHS, QWERTY versus Dvorak. Through local network effects and positive feedback, one option gains a slight advantage. This correlation amplifies until it becomes the dominant coherent standard across the entire population. The system has locked into a specific configuration. When you witness a system that can exist in a disordered phase, and then, with a small change in conditions, suddenly snap into a highly ordered, coordinated state that acts as one, you are seeing the hallmarks of field configuration and coherence. You are seeing grammar creating chapters from words. We must connect this culmination deeply to our holophase journey. In the previous part, interference showed us how waves can create patterns. Here, field configuration shows us how those patterns can become permanent, dominant states of being. We haven't added a new force of coherence. We've applied the existing rules of phi correlation and amplification to see how they can lead to phase transitions and ordered states. This is the holophase language, generating the very states of matter from which our world is built. If you want to see the full mathematical derivations and exact equations behind this idea, the formal definition of correlation functions and order parameters, the Landau-Ginzburg theory of phase transitions, the renormalization group analysis of critical exponents, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause and behold the vista of Book 9.3. We began with pure tones, dispersion, learned to make musical notes, packets, discovered harmony and counterpoint, interference, and finally arrived at the sustained orchestral symphony of a coherent field. We have completed the wave and field production engine. We now understand how the universe writes both the solitary whispers and the grand unified choruses of reality. In the next part, we cross a major frontier. We leave the descriptive realm of how waves and fields are configured and enter the explanatory realm of why. We begin Book 9.4, Dynamical Grammar. Here, we will encounter the central organizing principle of dynamics, the action sphy. We will learn that the universe doesn't just write random stories. It writes stories that extremize a certain narrative cost function. From this single principle, we will derive equations of motion, uncover deep links between symmetries and conservation laws, like energy and momentum, and introduce nonlinear interactions where waves truly converse and change one another. The grammar will become not just generative, but selective. Before we end, the mandatory zoom out to hold our scope. Coherent fields, phase transitions, correlation lengths, these majestic concepts are still just patterns in phi and its correlations. We have added no new substances. We have only read deeper into the grammar, learning how relationships between different parts of the phi field can, under the right conditions, create global unity from local rules. One field, phi, plus its infinite tower of derivative questions. In this episode, we have journeyed from the first sentence, through topological production, knots and braids, through the complete wave production engine, tones, words, grammar, and narratives. We stand ready to ask the most profound question of all. Why this story and not another? As we conclude, hold the image of the stadium wave of light. It began with isolated random twinkles, local ripples in the social field. A simple rule of local imitation propagated correlation. A threshold was crossed. Spontaneously, a direction was chosen, and a coherent, sweeping wave emerged, uniting the entire assembly into a single, beautiful display. The universe is this stadium on the scale of existence. The holophase field is the medium. The particles, atoms, and forces are the participants. And the field configuration rules are the subtle grammar of interaction that, when the conditions are precisely right, compels them to stop whispering alone and start singing together. In the laser's beam, in the superfluids flow, in the magnet's pull, in the very order that makes reality coherent, stable, and knowable. Salam, and peace be upon you.